Good afternoon. I'm Bugeja from the Malta College of Arts, Science and Technology, and today our paper is based implementing real-time monitoring and condition-based maintenance systems for electrical machines. So, introduction about the subject. So, the industry today bases more about Industry 4.0, which consists of sensors, implementing sensor condition-based maintenance on machines, electrical machines mainly, and to reduce downtime of the machines, increase performance, and increase a higher efficiency of the plant. This is based on electrical machines because modern industry uses them a lot for production and automation. So the main motor used is an induction motor, as seen here. So although it is very robust, a simple construction, however faults may develop. And here are the main faults that can develop from the induction motor, namely stator faults, rotor faults, bearing faults, which is the most trivial fault, which is the most dominant fault of the induction motor, and there's the eccentricity faults. Now, in this paper we used 3 techniques to detect these faults on the induction motor, namely the motor current signature analysis, which is used using spectral analysis, and to detect eccentricity faults, bearing faults, broken rotor bar faults. We used also another analysis tool was vibration analysis, namely to detect eccentricity and bearing faults. Also, thermal protection is important to prevent catastrophic failures from the stator winding insulation short circuit. So, our system is to develop a GUI for the user, as a smartwatch for the user, and also monitoring the condition of the motor. So we have the 3 main condition monitoring of the motor, a data acquisition board, and this will transfer wirelessly to the smartwatch, to the user, to the GUI, and to inform the user that a fault condition has happened on the motor. Also, real-time sensor data can be also monitored through the GUI of the smartphone. So, our block diagram is based around the NRF52832 microcontroller, which has the GUI for the user, this interface, a power monitoring system of the battery, and also was used this microcontroller because it has an integrated radio module that will benefit in PCB size area, and also it is mainly a very low cost microcontroller. So, another important factor of any smartwatch is to develop and monitor low current from the battery to minimize current consumption. And here, the first prototype that was done was to monitor the power from the battery. So this IC charges the battery, monitors the battery state, and also provides power to the system, to the smartwatch system, from various 2-buck converters and linear regulators. Also, this can be used to inform the microcontroller that some fault condition has happened to the battery. So this was the smartwatch developed PCB, and here is the main microcontroller, the antenna circuit to be able to receive data from the controller data acquisition board. Also, here we have connection for the LCD, the battery connector, and also here we have the power management system IC to manage all the various peripherals of the system. Also, a flash memory was used to store information to display later, as we will see. So this is the developed smartwatch. Another important factor consideration was the placement of the antenna, because we did not need that the antenna will be affected by metallic parts over and under above it. So this will decrease performance of the antenna. So placement consideration was important when deciding various placements of various components. So the data acquisition, so we have the three main: the condition monitoring of the motors, thermal protection, current sensing, and vibration monitoring. This is again the data is acquired by the microcontroller and is sent through wireless transmission to the smartwatch. So this is the main acquisition controller, and here we have sensors, temperature sensors, accelerometers, and the current sensing circuit that will be monitored by the microcontroller. So this is the hardware developed. So we have here temperature sensor ICs, NM's accelerometer to monitor vibration, and here we developed a three-phase, fully isolated, for each phase obviously, current sensing circuit. This was possible to use this measuring technique, the shunt-based measuring technique, because it was a low power motor that we create current from it. So power loss from the resistors was quite strong. So this another important factor was to tune the antenna circuit to achieve best performance when data is transferred from the data acquisition board to the smartwatch. This will increase range for the user and better performance of the system. So here we used here a Smith chart to calculate the components needed to match the transmission line to the 50 ohm impedance of the antenna. So here is the performance that we achieve from that circuit, where we can see the return loss of the, here is the data acquisition board and the smartwatch antenna. So we used the VNA to measure that return loss, and we achieved approximately 99%. That was the power absorbed by the antenna, so it was a successful circuit measure. So then we tested the motor to simulate an off-centric load. This will simulate a bearing fault, which is the most dominant fault on these induction motors. So we used an off-centric load, which is quite small, and here we tested also with an extreme off-centric load to see the differences in performance of the motor current signature analysis, vibrations, or analysis that we did. So here we see the results for 600 RPM with an off-centric load, and here the difference was negligible from the no fault condition to the off-centric load when using a motor current signature analysis. However, here we see that harmonics, the amplitude and increase in harmonics when an extreme off-centric load was triggered. And vibration analysis here, you can see that it's more pronounced and can be detected quite easily with this increase in harmonics and also in the time tone. With an extreme off-centric load, can be detected much easier, and here we can see the differences between a small off-centric load and an extreme off-centric load. And here the GUI that tests the user in real-time monitoring of temperature and also vibration data. And here we developed alarms to tell the user that a fault condition has settled on the motor. And that's the end of the presentation.
If there are any questions.
I have one. I was trying to understand this during the presentation. Why is smartwatch for this? You can have a sensor streaming data to a cloud, and then you see an app in mobile, or even in an app in a smartwatch. Why?
Yes, but it's this. And the challenge of developing a smartwatch also because this smartwatch is low cost compared to modern smartwatches. You have to say they cost more than 300 euros. This is a low cost solution
I
for the
understand,
smartwatch.
I understand, but I'm assuming that many people already have a mobile, and so the question I was posing in my head, maybe it's wrong, but it's why don't we stream this data to cloud and then access either on the smartwatch with an app or
Yes, it can be done also, but by that I think that I supports Bluetooth, so a connection to a mobile phone can be done, but that was a prime concern.